From the standpoint of cybernetics, air defense represents a complex integrated structure in which numerous informational, material, and energy flows are intertwined, requiring coordination and regulation with speed and precision sometimes inaccessible to humans. Control is the process of interaction between control organs and control objects, during which the circulation and processing of information characteristic of this process take place. Modern conditions require comprehensive improvement in the promptness, effectiveness, and reliability of control, for which automation is necessary, implying the integrated use of appropriate scientific methods and automatic devices. The essence of automation lies in transferring labor-intensive control tasks to electronic computing and other equipment, while preserving the role of human creative intellectual activity. Automation is preceded and accompanied by mechanization of troop control, which consists in the use of auxiliary technical means to perform only mechanical tasks in order to reduce the time expenditures of commanders and staffs on non-creative activity. Automatic control systems assume minimal human participation. In the system of controlling troop actions, due to its specificity, decision-making is a purely creative process. The main function of control, the making of the final decision, remains with the human commander. Therefore, no system of troop control can be completely automatic, though it must be maximally automated. Soviet military science exposed and rejected bourgeois concepts of the electronic commander and the push-button war. Only the commander is capable of uncovering all subtleties and details of the combat situation, in finding the correct path to victory over the enemy. Even with the highest degree of automation, the commander remains the central figure, and the staff the main control organ. The commander makes decisions, while the staff plans combat actions. Technical means only facilitate the activity of the commander and staff officers in controlling troops. Automation technology assumes the time-consuming, formal intellectual processes, and thereby creates time for human beings to perform more important creative activities. Man and machine thus enter into new functional relationships, in which the positive aspects of both man and technology are utilized. From man, his universality, creativity, decision-making, and evaluative ability. From the computer, speed, accuracy, memory capacity, and the ability to process large volumes of information.
The problem's plain to see. Too much technology. Machines to save our lives. Machines dehumanize. I'm not a robot without emotions. I'm not what you see. I'll come to help you with your problems so we can be free. I'm not a hero. I'm not the savior. Forget
As was discussed in Part 1 of this series, ASURK-1 was a response to the incompatibility of surface-to-air missile systems and radars within the PVO. P-12 was employed by S-75, P-15 managed low-altitude engagements, conducted by S-125, and P-14 was largely relegated to S-200 sites. While all of these radars were optimized for the weapons they were designed to support, mixed battalions were very common. There was beginning to exist a need for a universal radar that could handle the detection, guidance, and target designation needs of all three missiles. In 1956, P-80, or Altai, was the solution. Assisted by 2 rangefinders and 4 PRV-11 height finders, the complete P-80 complex would prove to be exceptionally accurate even in conditions of extreme interference. Initially, formations equipped with the P-80 radar would go without automation. Centralized fire control was carried out via manual plotting board. Battalion commanders would denote free fire sectors, in which enemy aircraft were expected or had been already detected. But even this relatively simplistic methodology failed to keep up with large raids, featuring 2 to 3 targets per minute. This was due to the simple fact that battalion commanders could not receive and depict the overall air situation fast enough to translate that data into relevant fire direction. It should be noted that in these situations, it was not a lack of firing channels that diminished a unit's effectiveness. It was the inability to rapidly assign targets so as to prevent multiple batteries firing at the same aircraft that resulted in these exercises being deemed failures. Nearly a decade later, these lessons repeated themselves in Vietnam. When studying the conflict, a great deal of interest was directed at the performance of the venerable S-75. A myriad of engagements were analyzed, 2 of which stood out. They transpired on November 6 of 1966 and in January of 1967, both involving PQM-34A. In the first incident, 6 battalions opened fire simultaneously. 12 missiles were expended. The first 4 struck the target. The 8 that came behind them were wasted on debris. In the second case, 2 battalions fired 7 missiles at an identical flight. The optimal expenditure of surface-to-air missiles was determined to be a matter of life or death. If a battery wasted its resources on a relatively small portion of an attack, it would be incapable of responding to the rest of the raid. In the summer of 1982, the application of drones to deplete poorly coordinated Syrian air defense systems was observed prior to large IAF raids, leaving batteries unmasked and exposed, exactly as Ne-5 had predicted decades prior. In 1957, at Ne-5, a somewhat disjointed effort was underway to determine if it was possible to create an automated complex intended for use within the PVO, managed by a digital computer. In 1959, by order of the Ministry of Defense, requirements were outlined for a program designated Electron. It was expected that whatever came of Electron would be integrated at command posts, radar nodes, low-altitude control points, and fighter guidance posts. Scientists from Ne-2 PVO assisted by constructing a theoretical foundation to outline desirable integrations on future control systems. By the beginning of the 1960s, they had finalized methods for evaluating the effectiveness of automated command systems, a complete set of combat control algorithms, a multitude of strict requirements that were to be observed in the creation of prospective display systems, and a series of studies on how to best mitigate fatigue as well as human error. The speed in which the groundwork was established allowed for NE5 to conclude preliminary research with unprecedented haste. A.L. Lifshitz was selected by the State Committee for Radio Electronics to realize Electron. However, he was not alone in this monumental effort. The Zagorsk Electromechanical Plant, NE101, or the Research Institute of Automated Equipment, the Sverdlovsk Plant of Electrical Automation, the Podlovsk Electromechanical Plant, the Leningrad Directorate of Design and Installation Works, PMT5, and many other organizations would be mobilized and contribute their expertise. In April of 1960, the designation ASURK-1 was used for the first time to describe the complex. It was to be produced by the Zagorsk Electromechanical Plant. 3 years later, on July 3, 1963, it would be accepted into service and integrated with surface-to-air missile regiments. Similar to Vektor-2, which it was designed to support, a mobile trailerized variant would be adopted for use in Central Europe. ASURK-1 was to streamline and build atop the unified P-80 radar complex, ensuring that the data it collected was employed to maximal effect. In its most basic configuration, it allowed for the simultaneous tracking of 10 targets, and coordination of 8 battalions equipped with S-75. Issues still remained when it came to mixed formations, operating S-125. To resolve this complication, in December of 1963, NE101 took over software development, with the intention of producing a system that could coordinate S-125 and S-75 alongside one another. In April of 1966, at a plant in Sverdlovsk, a modernized variant began serial production, known as ASURK-1M. This repeated itself shortly thereafter with S-200. Originally, it was assumed that separate regiments operating the unique PVO 200 fire control system would employ the new missile, furnished with P-14 and the ARTU automated transmission system, but this did not materialize. S-200 almost immediately began to show up in increasingly confusing mixed regiments and brigades, resulting in a need to further modernize ASURK-1. Therefore, on the 30th of April, 1966, work began to further refine the system. In March of the following year, ASURK-1MA took its place, which allowed for 8 S-125 and S-75 battalions to be coordinated, while supported by a single battalion of S-200, which featured 5 firing channels. P-80 also saw the introduction of an additional radar cluster at this time. Once again looking towards the war in Vietnam and conflicts in the Middle East, such as the Six-Day War, the prevalence of electronic warfare was noted as especially interesting. It was determined that if automated command and control was to remain relevant, it had to cope with this very present threat. In 1968, the Minister of Defense and the Minister of the Radio Industry launched an initiative within the Research Institute of Automation, and NE2, to develop software that would allow for ASURK-1 to triangulate enemy jammers. ASURK-1P would be introduced in 1969. Like all ASURK-1 variants, it obtained all of its data from P-80. As the 1970s drew near, the air-to-ground playbook had once again evolved to cope with the missile age, emphasizing extremely low-altitude flight before popping up to strike the enemy. P-80 simply could not cope with this, and so the low-altitude engagement capabilities of ASURK-1 once again needed improvement. 3 low-altitude command posts, known as MVP-1N, were introduced by the Sverdlovsk Plant of Electrical Automation in 1970, which entered service in 1973. Alongside the continued development of ASURK-1, in 1962, the Zagorsk Electromechanical Plant began work on a new, exponentially more advanced automated command system, dubbed Vektor-2. This complex was a part of a larger initiative to modernize the battlefield management systems from the military, which resulted in the eventual adoption of a whole host of concepts proposed around this time, such as LUK, a higher-level command platform that will be discussed in a later video. In December of 1963, development of the software expected to be employed on Vektor-2V, a unique variant intended for integration with Vektor-1, was transferred to NE101. A decade of rigorous research and development would be spent attempting to realize Vektor-2L, for use with LUK, and Vektor-2V. They would be adopted in 1972 and 1973 respectively. This investment was beyond worth it. The final product would be capable of tracking 40 air targets simultaneously, with the ability to absorb tracks from LUK or Vektor, and vice versa. It maintained complete compatibility with formations operating ASURK-1MA, while providing automatic fire control for 14 battalions operating S-75 and S-125, with 2 of those units being S-200. Additionally, it could guide 6 flights of interceptors, meaning that Vektor-2 could hand off aircraft it was controlling for closer coordination and greater redundancy. This was also extremely useful for deconfliction and eliminating issues associated with inter-branch operations. The computing complex could offer suggestions on targets to prioritize and how to best organize interceptors, when supported by friendly aircraft. This program was devised by V.M. Ganeshev from NE2. It was said that the complex could effectively operate without human input if it needed to, which was likely somewhat exaggerated, but demonstrates just how impressed its users were with the level of automation present. Many of those who worked on ASURK-1 and Vektor would go on to assist OKB Zvezda in developing IT-MIVT, the first domestic multiprocessor computing complex produced within the USSR. In many regards, ASURK-1 was an extension of Vektor-2. It coordinated with fighters by receiving information from this complex, and operated exceedingly similar subsystems. Of course, its ability to analyze overlapping coverage and task batteries accordingly was impressive, but this was only possible using information relayed from above. ASURK-1MA and subsequent variants therefore are more accurately considered systems that sought to expedite target prioritization, and eliminate the likelihood of multiple independent launches against a single target, rather than a comprehensive automated command and control system. However, there were still some additional lesser-known capabilities that are worth considering. The system allowed for far greater logistical efficiency, as prior to an interception, using the information gathered from its subordinate radar nodes, the expected expenditure of munitions was calculated, so that rear services could prepare for delivery within short order. It also allowed for electronic warfare systems on the ground to be coordinated alongside surface-to-air missiles, for both defensive and offensive purposes. The actions of the brigade commander and his chief of staff, like the first iteration of Vektor-2, remain largely manual. But with the assistance of the many automated workstations surrounding him, he can better coordinate his subordinates. Commands are transmitted faster and targets he assigns priority to are replicated at each battery. The fastest aircraft are generally engaged first, after which priority shifts to aircraft attacking the formation electronically. Once those targets have been eliminated, those who are being protected by the jammers are fired upon. If the raid is relatively small and consists of 10 or less targets, each radar node coordinates its batteries independent of the commander. This also applies to low-altitude targets, which are engaged the moment the opportunity to do so presents itself. The probable flight path, displayed on each screen throughout the formation, is updated and refined every second. The single number assigned to the target receives an update every 8 seconds. The trajectory is ultimately more important than the exact position of the aircraft, as it determines in the computer which battery will be selected to fire at the target first, due to how overlapping coverage is displayed. The trajectory and likely time of intercept will be used to ensure that missiles are launched in advance, and therefore have a high chance of striking the target once it reaches the optimal engagement envelope. When a large number of targets is present, as to not overwhelm the system, a track is dropped once it has been fired upon. This does not mean that the target disappears and is forgotten by the battery engaging it, but instead it is removed from the commander's display to ensure that he can focus on the aircraft that have not yet been attacked. Another feature provided to commanders, to streamline the coordination of mixed formations, is the ability to assign certain targets to batteries operating missiles that are more likely to succeed in destroying them. For example, targets at great distances and high altitudes are engaged by S-200, high-altitude targets at shorter ranges S-75, and targets at low-altitude S-125. Of course, this only applies if there is a considerable amount of overlapping coverage between different missile systems. No matter the target, if a missile is capable of engaging it, it is generally expected to do so. If a target executes evasive maneuvers, it is to be fired on by multiple batteries from various directions, or one battery in the direction the aircraft is defending. This is only done if there is no possibility of this limited attention shift, allowing aircraft to get through. Interestingly, to combat the limited automation present within the system, 10 commands can be pre-programmed into the computer before an operation begins. This allows for common actions the commander would usually engage throughout the course of an interception to be carried out with greater haste. saving manual interaction for more complicated situations where careful direction is required. A relatively advanced feature present within ASURK-1 is the ability to automatically subordinate batteries to neighboring formations to exploit their radars if the target is impossible to observe with local systems. This is handled by the formation's communication specialists, who have their own cabin equipped with relevant switching equipment. ASURK-1 gathers data through the harmonization of a myriad of radars attached to the brigade, such as P12, P14, P35, and P37, or P35M depending on how you like to reference it, and PRV-11 height finders. ASPD-1 will be provided to radar nodes located on the outskirts of a formation's coverage to speed up interaction. In the brigade's command cabin, UOT-1 and UOT-2 displays are present. Secondary displays known as UI-1 are also available, alongside a USD screen for depicting the overall air situation. This is also where the main digital computing complex is stored. The UOT-1 and UOT-2 are especially important, as they depict target coordinates. 10 contacts can be displayed on a single UOT screen, meaning that a total of 20 contacts can be actively observed by the formation. According to the Fire Control Manual, it is possible to depict an additional 2 arbitrary targets per screen, totaling 24 contacts. It is assumed that these will be dropped and replaced with great consistency, with some material on the matter stating that 60 to 180 seconds is standard. UOT-1 and UOT-2 can also receive information from ASPD-1 at a scale of 200 to 600 kilometers. The UI-1 displays are used to visualize speed and altitude. The secondary application of them is to determine the condition of each battalion subordinate to the brigade. The USD screens, of which there are 2 at this level, are managed by the brigade's radar operators, who, with the help of a joystick, designate up to 5 targets respectively. The formation communicates through R309-1 and R309-2 radio stations, and an R194M telephone switchboard. A set of R109M is also present alongside a series of TA57 field telephones at every relevant workstation. The brigade's central radio relay is made up of 2 antenna vehicles, a power supply station, and an R409 radio relay. All of these systems function in many regards identically to the subsystems discussed in Part 1, and so I will not be covering the technical characteristics here. Every action within the command post is recorded by a dictaphone, so that it can be reviewed later. This primarily serves to monitor training endeavors, but can also be used to pinpoint an error in the command process that may have led to an accident. This was a standard feature across all Soviet air defense command and control systems. In September of 1983, when 2 US aircraft were shot down by a mixed Syrian air defense formation, operating 2 S-200 battalions and 1 OSA battalion, this integration proved exceedingly useful. Shortly after this incident, the formation's command modules were confiscated and shipped back to the USSR for review. The next day, it was determined that the crew's actions had been justified, and the system was returned. Each battalion subordinate to the brigade, equipped with ASURK-1, will be accompanied by what is known as a coupling cabin. Here, the readiness of the battalion is coordinated, and commands are transmitted to a missile guidance station. The cabin receives information through a relay 500 meters away. This relay is always placed at the highest point in the area, where trees and civilian dwellings cannot obstruct it. In a similar fashion to RTBs within a unit equipped with Vosduke-1, battalions in ASURK-1 formations function according to a series of readiness postures. When the battalion is shifted to readiness number 1 and is assigned a target, its commander, using the information provided by his automated workstation, tasks his batteries. The guidance officer locates and tracks the targets the battalion has been assigned, and prepares for the system to switch to manual tracking if something goes wrong, or the unit is attacked and loses its automated capabilities. This is known as small sector search mode. The plotting board operator, using his TA57, receives information and depicts it accordingly. The battalion communicates using R309 radios. This is how the readiness of each battery is established and non-automated commands are transmitted. The battalion commander is provided with a series of commands he can transmit with the press of a button. The most important is launch carried out, which informs the brigade he has engaged a target assigned to him, and they are to drop the track and provide a new set of targets immediately. This process is automated, as is the provision of a new target. If the engagement was successful, the target destroyed switch is engaged, followed by receive target assignment, and shortly thereafter, processing of target assignment. If he has failed to destroy the target, he engages target not destroyed. which is done to shunt the immediate delivery of a new set of targets. If more information is required, the battalion commander has access to a switch labeled Fire Prohibition, which informs the guidance officer to continue tracking the target and that he is to relay all of its characteristics to him. If the battalion cannot destroy the target, the commander immediately engages with Draw Target Assignment. Switches labeled In Preparation and Launch Ready are present to indicate the battalion's readiness to the brigade during and after missile replenishment. The commander also has switches to determine the number of missiles that are to be fired at a target, which scale from 1 to 3. It is possible for a battalion to reposition in short order to a prepared or unprepared alternate position, before or after an interception. When breaking down the automated workstations present within the coupling cabin, the computing officer takes charge and oversees the transition to a march-ready state. The unit must then calibrate the equipment before it is possible to interface with the brigade, which can be a lengthy process, requiring a great deal of recalculation and topographic measurements. If passive jamming is detected by the formation, the targets being protected by the interference are identified, as is the source of the disturbance. If the signal of the jamming carrier cannot be observed, the radar operator tracks the center of the leading edge, the jam sector. The altitude of the jamming aircraft is determined in a similar fashion by using the upper edge of the sector. This allows the system's computer to form a somewhat accurate estimation as to where the target actually is. If the protected targets cannot be observed, the unit's height finders will be tasked with independently searching for them. If they detect a target, they will transmit its coordinates to the radar operator. This allows for the computer to process a relatively accurate set of coordinates for its engagement. If the P-35 or P-12 radars are attacked by active interference, the unit's height finders will begin an independent search. If both the height finders and early warning radars are jammed, the formation will shift to semi-automatic operation and manually determine the location of the air contacts using their plotting boards and the last known position of the enemy. When engaging a group of aircraft that have merged together into one contact due to insufficient resolution, batteries are assigned to fire at its center, the coordinates of which are determined by the brigade's command post. If it is possible to see individual targets within a group, it is standard practice to engage the first to enter its range of the battery. If several targets are approaching, all equidistant, the leftmost aircraft will be engaged, after which the rightmost target is prioritized. However, before ASURK-1 can do anything, its crew must establish 2 control points, which create a likely approach sector. This is extremely important, as without these control points, the formation's radars would have no way of determining what must be displayed on the USD screen. Vektor-2 is less of a successor to ASURK-1 and more of a sister system to Vektor-2. They share many of the same subsystems and were introduced alongside one another when purchased by Warsaw Pact customers. Unlike ASURK-1, which can be used to automate a regiment, Vektor-2 is almost exclusively employed by brigades. Vektor-2V, which is intended to operate alongside Vosduch-1M, is capable of processing 40 air targets, and as discussed above, can coordinate 14 S-75 and S-125 battalions. The system is also capable of cooperating with one ASURK-1MA equipped regiment, or brigade. When this is done, Vektor-2 uses its superior computing power to process commands for the ASURK-1 formation, before transmitting them to the unit's commander, so that he can carry out the task. It will also reflect all of the data it collects. The ASURK-1 formation will then reflect all of its data back. Vektor-2 can also exchange data with two neighboring formations. The most impressive feature of this complex is its ability to independently guide 6 flights of fighter aircraft. This not only frees up Vosduch-1M equipped formations above Vektor-2, but also allows for exchange so that these aircraft can closely cooperate with SAM systems and deconflict. 2 remote fighter control stations can also be established, which are capable of an additional 3 control processes each. So, technically, with a full accompaniment of fighter control stations, a Vektor-2 formation could guide 12 flights of aircraft. Vektor-2, like Vosduch-1M, is mounted on mobile trailers that can be repositioned with ease. 4 main trailers make up the primary control functions of the brigade and the system attached to it. These include the Automated Command Post, or KBU, the Computing Cabin, or KWK, the Communication Cabin, or KS, and the Radio Relay Cabin, which is technically composed of 2 trailers. These are supported by a mobile workshop containing spare parts and a power supply cabin, fitted with a generator. Interestingly, the radars employed by Vektor-2 are not a part of its native structure, and are provided by the radio technical troops, independently. The radar formation supporting Vektor is known as the PORI, and can be deployed locally near the previously described workstations, or remotely 250 kilometers away. The PORI is made up of an automated command post, designated KBUP, a computing cabin, known as KWKP, and a communications cabin, designated, you guessed it, KSP. Vektor-2 is so unbelievably similar to Vosduch-1M that many of its characteristics have already been discussed in Part 1, considering that they both employ APN-1M and function in tandem with one another. But there are still some unique aspects that warrant discussion. The entire complex can be switched on, for operation, in just 6 minutes from mains, and 8 minutes from a generator. If powering up in an accelerated combat fashion, this drops to 1.5 minutes from mains, and 3 minutes from a generator. For the PORI, a startup time of 16 minutes from mains is to be expected, which increases to 19 minutes from a generator. When accelerated, this can be done in 6 minutes. The entire complex can reposition in just 2 hours and 40 minutes on average. Vektor-2 can process a single target in 30 seconds. If electronic interference is present, the manual states that this increases to 50 seconds. If Vektor-2 has to process 40 targets at once, which is unlikely, this can be accomplished in 120 seconds. A command can be generated and distributed in 10 to 20 seconds, while a target can be handed off to a battery for engagement in 20 to 24 seconds. Commands are always transmitted through both wired and relay communications when possible to maximize the chance of reception. The system can plot planar coordinates in 10 seconds and altitude in 60. The probability of accurately distributing targets throughout a formation is stated to be 0.9. The likelihood of designating a target that is not jammed or maneuvering is 0.95. If the target is maneuvering, this drops to 0.8, and if jamming is present on top of this, 0.7. It is possible to plot and designate 15 jamming carriers, as they are denoted by the system. It is possible to conduct triangulation on all 15 of these aircraft simultaneously. The primary automated command post, which I will reference as the KBU moving forward, handles the automated transmission of fire control commands. There are 14 workstations present at this level, half of which are automated. They are broken into 3 variants, Type 1, Type 2, and Type 4. There is an equal distribution of Type 1 and Type 2, but only one Type 4. All workstations display information via a 45cm cathode ray tube. They only differ in the engraving of the anti-parallax plexiglass plate and the input panels. Type 1 stations are for issuing commands to anti-aircraft missile battalions. and the automatic slewing of batteries towards designated targets, while Type 2 transmits commands to fighter aircraft. There only needs to be one Type 4 workstation, as its role is to input data onto the overall air situation map. Type 1 and Type 2 workstations can run two programs: IKO mode, or the general display, where the radar scope is depicted, and target distribution mode. Normally, everyone operates in IKO mode, but the Chief of Staff and Senior Navigator, as well as the Fire Control Officer, operate in target distribution mode. In this mode, the screen displays a rectangular deflection. Along the vertical axes, the approach time to the kill zone is plotted in scales of 600 and 1,200 seconds. Along the horizontal axis, the missile battalions subordinate to the formation and any cooperating ASURK-1 MA unit are shown. The computing cabin, or KWK, houses Vektor-2 computers, which function in what is referenced as alternating hot standby mode, which is especially interesting. One computer performs calculations, while the other is synchronized and running the same program. Every 10 seconds, they exchange information and switch roles. Therefore, if one computer fails, the other can immediately take over without delay. To accomplish this, there are two program exchange devices, which, like the computers, operate alternately. Why they did not just have one running all the time and the other on standby mode is unknown to me. Maybe it had something to do with Soviet workers' rights, and computers had union-regulated breaks. All jokes aside, it was likely to make the turnover time faster in case one was damaged or shut down, though this does worry me about the reliability of these computers if this was genuinely a huge concern. These computers operate on a binary system, with a 20-bit word length. 19, 20, and 21-bit architectures were common in the USSR at this time, especially when it came to microcontrollers. These computers were capable of 40,000 operations per second, and could receive 74 instructions. They had a capacity of 8,192 words, but housed 32,786 for programs, 7,168 for constants, and 256 for variables. The exact computer used in Vektor-2 is unknown to me, and there is no source that I know of that accurately describes which computer variant this was, though I have a feeling it was likely an Argon variant. Possibly Argon 15, but the specs don't line up. This is likely a factor of me not having access to Cyrillic manuals for Vektor-2. It's highly likely that the East German manuals that much of this information is coming from describe a different computer, considering that many air defense control systems in the 80s used Argon 15. I have a suspicion that it was likely Argon 15 in Soviet service, and whatever is being mentioned here was unique to East German service, but that is just a suspicion of mine. I cannot confirm anything for certain. The communications cabin is equipped with 4 R-824 stations, 2 for fighter guidance and 2 for voice communication with aircraft controlled by the formation. Like in Vostok-1 and Vostok-1M, when data is received and converted for display at the KBU, it is rescaled to be positionally relevant. This is managed by a coordinate conversion computer. Compared to ASURK-1MA, Vektor-2V served as a quantum leap in air defense capabilities, with the exception that it had to be attached to a wider air defense formation to exploit these improvements. Before I conclude this video, which was relatively short, and generally serves as an extension to the first video in this series, I would like to include an amusing anecdote, which was not present in Part 1, regarding initial Vostok-1 trials. Back in 1964, we intensively studied characteristics of communication channels, provided by the military for transmission of digital information, in the automated command system Vostok. We conducted statistical studies of practically all types of channels: wire, radio relay, and tropospheric. For this purpose, special devices were manufactured. statistical analyzers of communications channels. The results were depressing. The cause was not so much shortcomings of communications equipment, as it was the methods of organization of communications, and the low qualification and discipline of serving personnel at that time. At the initial trials of ASURK in 1964, I, as a signalman, was shocked by a situation where dozens of heavy field multi-core cables were laid between command posts. Many of these cables were connected with couplings, since the length of a single cable was not enough. All of this was thrown into wet snow. The consequences were sad. Moisture penetrated into the connectors. Telegraph pulses with voltage of plus or minus 60 volts led to corrosion of contacts. Interference that arose in the cables disrupted both telephone and telecode communications. To transmit telecode information via Vektor-2, telegraph apparatuses were used. From the standpoint of communications, this too was barbarity, since equipment already existed that ensured transmission of pulse signals at a speed of 1,200 bits per second. But the chief designer had no time to delve into this problem. Such communication decisions had been made by a Moscow institute. They were optimal. For the chief designer, communications was an inevitable evil, which one had to put up with, and sometimes one could shift their sins and miscalculations onto bad communications. Again, I apologize for the length of this video. It is the shortest one I have released recently. The reason for its brevity was the result of extreme similarity between these systems and what was discussed prior. They use basically all the same components, and they were developed in tandem, so there isn't a whole lot to say, but they are very important and worth discussing. And the interoperability of these complexes is rather interesting, so I wanted to dedicate a video to it. Expect something on Orbita or Almaz to be out in the next few weeks. I hope this was enjoyed despite its length. Wenn je